This video refers to Lecture 6, Structural Analysis, specifically the third part of that method of sections for solving the forces inside members. And if you look at slide 21, it shows you two pictures, one of a crane and one of an electricity pylon. And it gives you an idea that these truss structures can be very, very large. Using method of joints, where you find the force in every member, can be very, very slow. So rather than where in method of joints we assume that if the structure is in equilibrium, every joint is in equilibrium, in method of sections we can divide along an imaginary line the truss into two sections and only focus on a smaller section. And we assume that if one section is in so if the whole truss is in equilibrium, each section is in equilibrium. And just to give you another thought, if that's a member that is being stretched, and I cut it in half, then each half is also being stretched like a magnet. Okay, don't get these arrows confused with what's happening at the joints, where the arrows are actually the other way around. But if I'm stretching one member, then I'm stretching each half member by the same amount. I think the easiest way to work out what's happening is to actually look at an example. So I'm going to look at the example on slide 26. And that's got rather a large truss section, which is going to take a long time to draw, and is asking you to calculate the forces only in members KJ, KD and CD. I'll have a go at drawing it and then show you what to do. Okay, so I cheated there slightly and found how I could get a photo of that into the video, but never mind. You'll have to draw it for your notes, or print it. So the first thing we do before we cut down our imaginary line is we work on the truss as a whole, and we can see we've got a pin joint at A and we've got a rolling joint at G. And we start to analyse, well, what's happening in those different points. So we could have force here, AY, we could have a force, we don't know which way it is, but we'll call that AX, and we can have a GX, a GY, but there's no GX because it's a rolling joint. Now the only force acting in the X direction is AX in this question. There's nothing else pushing or pulling it in the X direction, therefore we can say AX equals 0. Then we can find our forces at either AY or GY, or indeed both. We're only going to focus eventually on the left hand side of this. You'll notice the imaginary line cuts through the three members that we're interested in finding the forces in. However, the left hand side has fewer members to consider and to deal with, so we'll focus on the left hand side with AY. If we want to find AY, we can take our moments about G, because then we can ignore our unknown GY. So the sum of our moments is going to equal AY times 18, because it's 18 metres away from point G, and it's going, that's actually turning clockwise, so that should be a minus, plus 20 times 15, plus 30 times 12, plus 40 times 9. And that all has to equal 0 to be in equilibrium. We can therefore say AY is equal to 56.7 kilonewtons. So that finds us the external, the reaction force AY. So we're actually looking for the forces in members KJ, KD and CD. Well, two of those members pass through the point D. So the forces the members are interested in are this one, that one and that one. And obviously KD and CD pass through point D. So the easiest way to ignore them, to ignore those unknown forces, is to take a moment about point D. So I'll keep jumping backwards and forwards, but you may want to refer to the slides with the diagram. our moment, whoops, I left it in green, our moment about point D, we've got AY, which we know, and that is 9 metres away from point D, and that's trying to go clockwise, so it's minus. We've got 20 kilonewtons trying to go anti-clockwise, so it's positive. We've got 30 newtons trying to go anti-clockwise, so it's positive. And then we've got a force which, if we go back here in kJ, if we label it, and we label it that way to start with, that's our assumption again, it's going to be negative FKJ, and that's 4 metres away perpendicularly. So that's in another colour. That's 4 metres away from point D perpendicularly, i.e. here. So I can then rearrange that, and I can find FKJ to equal minus 75.1 kilonewtons. So we originally assumed it to be in tension. It's pulling away from joint K. We've actually found it's negative. We've got a negative answer, so it must be 75.1 kilonewtons in compression. I don't know why I put a bracket there. That's very confusing. Okay. Now we've got that, just for our section, we can use some of the forces in the X and the Y direction to do the rest and to find our other two unknowns. So in the X direction, we're going to have minus 75.1 plus 3/5 of FKD, and that's assuming some directions. So that's assuming that they're all pointing that way. And that's equal to 0. And our sum of our forces in the Y equals... Hang on, I've missed a bit, apologies. In the X we've also got FCD, haven't we? So we can't solve that one straight away, but we can sum the forces in the Y. It's going to be 56.7, and it's positive because it's going upwards. Minus 20, minus 30. We don't need the minus 40 because the minus 40 sits in a different section. Minus 4/5 of FKD equals 0. So FKD equals 8.38 kilonewtons, and that's in tension because we assumed it was in tension and it came out as positive. We can then substitute FKD back into the sum of the forces in the X, and we rearrange to get FCD equaling 70.1 kilonewtons, and that's also in tension. So just to sum up, whoops, too far, we took our diagram, we found our reaction forces AX and AY. And we did that by considering the truss as a whole. We then focused purely on one section, so the left-hand section, but we took a moment about a point in the right-hand section, but we only used the forces from the left-hand section because it's in equilibrium. If the whole thing's in equilibrium, we assume each section is in equilibrium. We found the forces in one member, and then we used the sum of the forces in the X and the Y direction to find the forces in the other two members we were interested in. So that concludes the example. There's now one for you to have a go at, which begins on slide 31. So if you have a go at that question and then come back to the video and I'll show you how to solve it. So you should have to go at the group problem solving exercise beginning on slide 31. So this is how you would then go about solving it. you're asked for the forces in members GB and GF. Clearly you can't put an imaginary line down where just two of those forces that would cut just those two members. However, you can cut relatively few if you put a line across there. So that's the imaginary line that you would add on to minimise the amount of work to do. Next thing you do, similar to before, is you work out the external forces. So we're going to have an AY and an AX, and we're going to have a DY over here. However, we're not going to be worried about DY, just as we weren't worried about the G part earlier. Similar to earlier again, our force in the X is AX, which is nothing, because there's nothing pulling it apart from that potential support reaction there. So AX is 0. Our moments about point D will find as AY. So that's going to equal minus AY times 28. It's a minus because it's going to try and turn it anti-clockwise about point D. 600 times 18, because the 600 kilonewtons is turning it, the AY is turning it clockwise, the 600 is turning it anti-clockwise, so therefore it's positive. And 800 times 10, because again that's going to want to turn it anti-clockwise, so we're going to call that positive. That all equals 0. So we can get AY to equal 671.4 kilonewtons. So that finds us our external force in the section we're interested in. Now we only need to analyse the left section again. So if we draw on some assumptions, if we assume FGB is going that way, and FGF they've assumed in the notes is going that way, the final assumption you're going to make is that FAB is going that way. Okay, so they're the three members that are cut along our imaginary red line. So what we'd then do is we'd have moments. The best place to take a moment about, well, two of our forces, FAB and FGB, pass through B, so we can ignore them if we take moments about B to start with. So some of our moments about B is going to be minus 671.4, which was our AY, and that's 10 metres from B, which you can see just here. We've also got FGF, which is also 10 metres from B, and going the opposite way. Go back to black. So FGF comes out at 671.4 kilonewtons. And our assumption was shown to be right, so FGF is in compression. Now we can simply sum the forces in the y direction to get FGB, which is the only other force we're interested in. So forces in the y are going to be 671.4, which is AY, minus FGB. So FGB equals 671.4 kilonewtons. We've assumed it to be in tension, it's coming out positive, therefore it's in tension. So that concludes the method of sections part of the structural analysis videos. Hopefully it's not too disjointed with the piecing together in the middle. There's one final section looking at the applications of some of these in terms of frames and machines, which will be video number 4 of lecture 6, which follows this.